I've been thinking a lot about galaxies, and it's one of those things that when you first hear about them, you think you understand what they are, right? A collection of stars, some gas, some dust, swirling around in space. Seems straightforward enough. But the more you dig into it, the more you realize that galaxies are some of the most complex, dynamic, violent, and frankly bizarre structures in the entire cosmos. And what's even more remarkable is that they're not eternal. They're born, they live, they die, they're destroyed, transformed, consumed. And the story of how that happens, well, it's one of the most epic narratives in all of science, spanning billions of years, involving forces so immense they're almost impossible to comprehend, and raising questions that strike at the very heart of existence itself. When you look up at the night sky on a clear evening, away from city lights, you might see a faint band of light stretching across the darkness, the Milky Way, we call it. And for most of human history, people had no idea what that actually was. Some cultures thought it was a river in the sky. Others thought it was milk spilled by the gods. It wasn't until Galileo pointed his telescope at it in the early 1600s that anyone realized it was made of stars. Countless individual stars too faint and too distant to see with the naked eye alone. But even then, nobody understood what it really meant. Nobody understood that we were inside something, you see, looking at it from within. It's like being inside a forest and trying to understand the shape of the forest from your position among the trees. You can see trees all around you, sure, but the overall structure, the boundaries, the form of the whole thing, that's incredibly difficult to piece together, and that's where we were for a long time. We knew there were stars, lots of stars, and we knew they seemed to cluster in this band across the sky, but we didn't know we were in a galaxy. We didn't even know what a galaxy was. There were these fuzzy patches of light that astronomers had catalogued, nebulae they were called, and some of them looked like little spiral shapes through the telescope. Beautiful, delicate, mysterious. But were they clouds of gas within our own star system, or were they something else entirely? That question, that fundamental question about the nature of these spiral nebulae, it sparked one of the great debates in astronomy. And the answer, when it finally came, it changed everything. It changed how we see ourselves in the cosmos. It was in the 1920s that Edwin Hubble, using the massive telescope at Mount Wilson Observatory, finally settled the question. He found a type of star called a Cepheid variable in one of these spiral nebulae, the Andromeda Nebula specifically. And Cepheid variables, well, they're like cosmic lighthouses. They pulse with a regular rhythm, and the speed of that pulse tells you how bright they actually are. And if you know how bright something actually is, and you can measure how bright it appears to be from Earth, you can calculate how far away it is. It's just geometry at that point. And what Hubble found was that this spiral nebula, this fuzzy patch in Andromeda, it was incredibly far away. Not thousands of light years away, not even tens of thousands, but millions of light years away. So far away that it couldn't possibly be part of our own collection of stars. It had to be something separate, another island universe, as they started calling it, another galaxy. And if Andromeda was a separate galaxy, then we had to be in one too. The Milky Way wasn't just a band of stars across the sky. It was our galaxy, a vast, disc-shaped collection of hundreds of billions of stars, and we were located somewhere out in the suburbs of it, about 2/3 of the way from the center to the edge. Looking toward the center of the disk, we see that dense band of stars. Looking perpendicular to the disk, we see far fewer stars, and we can see other galaxies separate from our own. The universe, it turned out, was far, far larger than anyone had imagined, and it was full of galaxies, billions of them, each one containing billions or even hundreds of billions of stars. But here's where it gets interesting, because once we knew what galaxies were, the next question became obvious. Where did they come from? How do galaxies form? And that's not an easy question to answer, because galaxies are old, really old. The light we see from the most distant galaxies, it's been traveling for more than 13 billion years to reach us. We're seeing them as they were when the universe itself was very, very young. And what we see when we look at those ancient distant galaxies is something remarkable. We see galaxies in the process of being born. We see the earliest stages of galaxy formation playing out across cosmic time. You see, in the beginning, right after the Big Bang, the universe was incredibly smooth and uniform. It was hot, dense, filled with a plasma of particles and radiation, and it was expanding rapidly. But it wasn't perfectly smooth. There were tiny, tiny fluctuations in density, quantum fluctuations that got stretched to enormous sizes, during a period called inflation. And those tiny variations, those little regions that were just slightly denser than average, they mattered. They mattered enormously because gravity amplifies small differences. If a region is slightly denser than its surroundings, it has slightly more mass, which means slightly more gravitational pull, which means it attracts more matter, which makes it even denser, which increases its gravitational pull even more. It's a feedback loop, you see, a runaway process that takes tiny initial differences and turns them into enormous structures over time. As the universe expanded and cooled, about 380,000 years after the Big Bang, something crucial happened. The plasma that had filled the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. And neutral atoms don't interact with light the way plasma does. Suddenly, the universe became transparent. Light could travel freely through space. We call this the moment of recombination, and we can actually see it. When we look at the cosmic microwave background radiation, that faint glow that fills the entire sky, we're seeing light from that moment, light that's been traveling through space for more than 13 billion years. And in that light, we can see those tiny fluctuations in density, frozen in time, the seeds from which everything that came after would grow. But here's the thing, the matter that we can see, the normal matter made of protons and neutrons and electrons, the stuff that makes up stars and planets and you and me, that's only about 15% of the matter in the universe. The other 85%, well, that's dark matter. We don't know what it is. We can't see it directly. It doesn't emit light or absorb light or interact with electromagnetic radiation in any way we've been able to detect. But we know it's there because we can see its gravitational effects. Galaxies rotate too fast for the amount of visible matter they contain. Galaxy clusters are held together by more gravity than their visible matter can account for. The distribution of galaxies across the universe, the large-scale structure of the cosmos, it only makes sense if there's much more matter out there than what we can see. And dark matter, it turns out, is absolutely crucial to galaxy formation. You see, in those early times after recombination, normal matter was still coupled to radiation. Photons, particles of light, they kept pushing on the normal matter, preventing it from collapsing too quickly under its own gravity. But dark matter doesn't interact with photons. It only interacts through gravity, so dark matter could start collapsing earlier, could start forming structures before normal matter could. And once the dark matter had collapsed into dense clumps, once it had created deep gravitational wells, then normal matter could fall into those wells. The dark matter provided the gravitational scaffolding, you might say, the framework upon which galaxies could form. So picture this, about 100 million years after the Big Bang, maybe 200 million years, in that period we call the cosmic dark ages because no stars had formed yet, dark matter halos were growing, pulling in more and more matter. And eventually, within the deepest of these halos, normal matter, mostly hydrogen and helium, began to accumulate. As this gas fell into the gravitational well, it compressed, it heated up, and in the densest regions, it became hot enough for nuclear fusion to ignite. The first stars were born. And once you have stars, once you have nuclear fusion happening, you have a galaxy, or at least the beginning of one. But those first galaxies, they were nothing like the Milky Way. They were small, irregular, chaotic. Some had only a few million stars compared to the hundreds of billions in large galaxies today. They formed in bursts, intense episodes of star formation that could light up these little proto-galaxies like cosmic fireworks and then fade, leaving them dark again until the next burst. And here's what's remarkable. We can see these early galaxies. With telescopes like the Hubble Space Telescope and now the James Webb Space Telescope, we can look so far into the distance, so far back in time, that we can see galaxies as they were just a few 100 million years after the Big Bang. We can watch the universe learning how to make galaxies, so to speak. And what we've learned is that galaxy formation is messy, it's violent, it's chaotic. Those early small galaxies, they didn't stay separate. They collided, they merged, they cannibalized each other. Gravity brought them together. And when galaxies collide, well, it's not like stars crashing into each other. Space is mostly empty, right? The stars in a galaxy are spread so far apart that even when two galaxies pass through each other, the individual stars almost never actually hit. What happens instead is that the gravitational fields of the two galaxies interact, stirring everything up, pulling stars into new orbits, triggering massive bursts of star formation as gas clouds collide and compress, and eventually, over hundreds of millions of years, the two galaxies merge into one larger galaxy. This process, this hierarchical merging as it's called, it's how big galaxies like the Milky Way were built. Over billions of years, small galaxies merged to form medium galaxies. Medium galaxies merged to form large galaxies. And all the while, gas was falling in from the intergalactic medium, feeding the galaxies, providing raw material for new generations of stars. It's a growth process, an accumulation of matter over cosmic time, and we can see evidence of it everywhere we look. The Milky Way has streams of stars orbiting it, streams that came from smaller galaxies that were torn apart by our galaxy's gravity, their stars pulled into long tendrils. We're eating smaller galaxies even now. In fact, there's a small galaxy called the Sagittarius Dwarf that's in the process of being consumed by the Milky Way at this very moment. Galactic cannibalism happening right in our cosmic neighborhood. But let's step back for a moment and think about what a galaxy actually is, what its structure is, because that matters for understanding how galaxies can be destroyed or transformed. Most large galaxies fall into one of a few basic categories. There are spiral galaxies like the Milky Way, with a central bulge of older stars surrounded by a flat disk, with beautiful spiral arms where young stars are being born. There are elliptical galaxies, which are more like fuzzy footballs or spheres, filled with old stars and very little gas, not much star formation happening anymore. And there are irregular galaxies, which don't fit into either category, often small, often distorted, sometimes because they've been disrupted by interactions with other galaxies. The spiral galaxies, they're particularly interesting because those spiral arms, those beautiful structures, they're not fixed. The stars in a spiral galaxy don't stay in the spiral arms. Instead, the spiral arms are density waves, regions where stars and gas temporarily bunch up as they orbit the galactic center. It's like a traffic jam on a highway. The cars move through the traffic jam, but the traffic jam itself, the region of high density, it stays in roughly the same place. In a galaxy, the spiral arms rotate around the center, and stars move in and out of them as they orbit. When gas clouds enter a spiral arm, they get compressed by the increased density, and that compression can trigger star formation. That's why spiral arms are bright and blue, full of hot young stars. The stars were born there recently, in the spiral arm, and they'll drift out of it later in their lives. And at the center of most large galaxies, there's something even more remarkable and more terrifying. There's a supermassive black hole. We're talking black holes with millions or even billions of times the mass of the sun, crammed into a region smaller than our solar system. The Milky Way has one, a black hole about 4 million times the mass of the sun, sitting right at the galactic center. We call it Sagittarius a star, and we've actually taken pictures of it, or rather we've taken pictures of the glowing gas swirling around it, the hot material that's about to fall in. These supermassive black holes, they're not just passengers in galaxies, they're active participants in galactic evolution. When matter falls into them, it heats up to incredible temperatures, emitting enormous amounts of radiation, sometimes more energy than all the stars in the galaxy combined. And that radiation, it can drive powerful winds that blast gas out of the galaxy, shutting down star formation. The black hole can regulate its own food supply, in a sense, by blowing away the gas that would otherwise fall into it. This is where the story of galaxy formation gets really complex, really interconnected. Because it's not just about gravity pulling matter together, it's about feedback mechanisms. Star formation itself provides feedback. When massive stars die in supernova explosions, they blast gas out into space, heating it up, making it harder for that gas to collapse and form new stars. Active galactic nuclei, those supermassive black holes actively consuming matter, they provide even more powerful feedback, potentially shutting down star formation across the entire galaxy. And all of these processes, they're happening simultaneously, competing with each other, balancing each other, determining whether a galaxy continues to form stars or whether it quenches, whether it stops forming stars and slowly ages. But we're supposed to be talking about how galaxies are destroyed, right? And that's where things get really dramatic, because galaxies don't just fade away quietly. They can be destroyed in spectacularly violent ways. And the most obvious way to destroy a galaxy is to crash it into another galaxy. Now, I said earlier that the stars don't actually hit each other, and that's true, but that doesn't mean galaxy collisions are gentle, far from it. When two large spiral galaxies collide, the result is chaos. The orderly spiral structure gets completely disrupted. Stars are flung into new orbits. The gas in both galaxies, the raw material for making stars, gets compressed and shocked, triggering an incredible burst of star formation, a starburst event where new stars are being born at rates hundreds of times higher than normal. And if the two galaxies are similar in size, they'll merge, slowly orbiting each other, passing through each other multiple times, losing energy to gravitational friction, spiraling closer together over hundreds of millions of years, until finally their central black holes merge and the stars settle into a new configuration. And what you get from the merger of two large spiral galaxies, more often than not, is an elliptical galaxy. The orderly disks are destroyed. The spiral structure is obliterated. What emerges is a more spherical distribution of stars. And because so much of the gas was used up in the starburst, there's not much left to form new stars. The new elliptical galaxy is filled with older, redder stars, and it's largely dead in terms of active star formation. So in a very real sense, galaxy collisions destroy galaxies, not by annihilating them, not by making them disappear, but by transforming them so completely that they're no longer recognizable. The spiral galaxies that went in don't come out the other side. Something new emerges, something different. It's a death and a rebirth at the same time. And this isn't rare. This isn't some hypothetical process. We see galaxies in the process of merging all over the universe. The antennae galaxies are two spirals in the middle of a collision, their shapes distorted, long tails of stars pulled out by tidal forces. The mice galaxies, same thing, long tails streaming out behind them like the tails of comets. Everywhere we look, we see galaxies interacting, disrupting each other, transforming each other. And the Milky Way, our own galaxy, it's not immune to this fate. In fact, we know with certainty that in about 4 to 5 billion years, the Milky Way is going to collide with the Andromeda galaxy. Andromeda is heading toward us right now at about 110 kilometers per second. It's inevitable. The two largest galaxies in the local group, our little cluster of galaxies, are going to merge. And when they do, the Milky Way as we know it will be destroyed. The spiral structure will be disrupted. The Sun and Earth, if they still exist at that point, will be flung into new orbits. We might end up much farther from the galactic center or much closer. We don't know. But the galaxy we live in, the Milky Way, it will cease to exist as a distinct entity. Astronomers have already come up with a name for the merged galaxy, Milkomeda, or sometimes Milkdromeda, a new galaxy, born from the destruction of the two that came before. But galaxy collisions aren't the only way galaxies can be destroyed. There's also something called RAM pressure stripping. Imagine a galaxy moving through the intergalactic medium, the thin gas that exists between galaxies in a cluster. Now, the intergalactic medium is incredibly diffuse, almost a vacuum by Earth standards. But when a galaxy is moving through it at hundreds or thousands of kilometers per second, that thin gas exerts a pressure on the galaxy, like wind resistance on a car. And that pressure, that RAM pressure, it can strip the gas right out of the galaxy. Not the stars are held too tightly by the galaxy's gravity, but the gas, the thin clouds of hydrogen and helium that fill the space between stars, that can be pushed out, blown away by the RAM pressure. And if you remove the gas from a galaxy, you kill it, not immediately. The stars that already exist will continue to shine for billions of years, but without gas you can't form new stars. The galaxy slowly fades as its existing stars age and die. It transforms from a vibrant, active star-forming galaxy into a dead elliptical or lenticular galaxy, a relic, a ghost of what it once was. And we see this happening in galaxy clusters. We see galaxies falling into clusters, and we can see the gas being stripped away, sometimes even captured in images as long streamers of gas trailing behind the galaxy like the tail of a comet. These galaxies are being murdered, in a sense, killed by their environment. There's also tidal disruption. If a small galaxy ventures too close to a large galaxy, The tidal forces, the difference in gravitational pull on the near side versus the far side, can literally tear the small galaxy apart. The stars get pulled out into long streams that eventually disperse and become part of the larger galaxy's halo. The small galaxy is completely destroyed, consumed, its identity erased. We see evidence of this around the Milky Way. Those stellar streams I mentioned earlier, the remnants of dwarf galaxies, that's tidal disruption in action, and it's happening constantly. Dwarf galaxies are being shredded and absorbed by larger galaxies all the time. It's a violent, a predatory universe out there. But here's where we need to think bigger, much bigger, because all of these processes, galaxy collisions, and ram pressure stripping and tidal disruption. These are ways individual galaxies can be destroyed or transformed. But what about galaxies as a class? What about the eventual fate of all galaxies? Because the universe isn't static, it's changing, evolving, and the far future of the cosmos holds even more dramatic forms of galaxy destruction. You see, we've known since Hubble's time that the universe is expanding. Galaxies are moving away from each other, and the farther away a galaxy is, the faster it's receding. Space itself is expanding, carrying galaxies along with it. But in 1998, astronomers discovered something shocking. They were studying distant supernovae, trying to measure how much the expansion of the universe was slowing down due to gravity. And what they found was the opposite of what they expected. The expansion wasn't slowing down, it was speeding up. The universe was expanding faster and faster over time. This was completely unexpected. It required a new component of the universe, something we call dark energy. We don't know what dark energy is. It might be a property of space itself, vacuum energy, a cosmological constant. It might be some kind of field permeating the universe. We don't know. But whatever it is, it acts like anti-gravity on large scales. It pushes space apart. And it's the dominant component of the universe now. About 70% of the energy density of the universe is dark energy. Dark matter is about 25%. Normal matter, everything we can see, is only about 5%. And dark energy changes everything when it comes to the far future of galaxies. Because as the universe continues to expand and accelerate, galaxy clusters, the large structures held together by gravity, they're going to become isolated from each other. The space between clusters is expanding so fast that eventually light from one cluster won't be able to reach another cluster. They'll pass beyond each other's cosmic horizons. From the perspective of someone in a galaxy cluster, the rest of the universe will fade away. First, the most distant galaxies will disappear, red-shifted beyond detection, then closer ones. Eventually, only the galaxies in your local cluster will be visible. The universe will seem much smaller, much lonelier. Within a cluster, gravity is strong enough to hold things together, at least for a while. The Milky Way and Andromeda will merge. Other galaxies in the local group will merge. Eventually, billions of years from now, all the galaxies in the local group will have coalesced into one giant elliptical galaxy. And that galaxy, that final merged remnant, will be essentially alone in the observable universe. All other galaxy clusters will have receded beyond the cosmic horizon. If there are astronomers alive then, they'll look out into the universe and see nothing, just their own galaxy, surrounded by darkness. But even that's not the end, because stars don't last forever. They burn through their fuel and die. The massive stars die quickly, in just millions of years, exploding as supernovae. Smaller stars like the Sun last billions of years, but they die too, eventually, swelling into red giants and then shedding their outer layers, leaving behind white dwarfs, cooling embers of what they once were. The smallest stars, red dwarfs, they can last for trillions of years, burning their hydrogen incredibly slowly. But even they will eventually run out of fuel. So in the far future, in tens of trillions of years, star formation in galaxies will stop. All the available gas will either have been turned into stars or blown out of galaxies by various processes. The last stars will be born, will live out their lives, and will die. And when the last red dwarf finally exhausts its fuel and fades to black, galaxies will go dark. They'll still exist, still be held together by gravity, but they'll be filled with stellar corpses, white dwarfs, neutron stars, black holes, dead remnants of stars that once shone brightly, dark galaxies invisible against the black backdrop of space. But there's more, because even these dark galaxies aren't stable forever. Over incredibly long timescales, longer than the current age of the universe by factors of billions or more, stars in galaxies undergo dynamical evolution. They interact gravitationally with each other, exchanging energy, and occasionally, through random gravitational encounters, a star will gain enough energy to escape the galaxy entirely. It'll be ejected, flung out into intergalactic space. This process, called evaporation, will slowly whittle away at galaxies over timescales of 10 to the power of 19 to 10 to the power of 20 years. That's 10 to 100 million trillion years, an incomprehensibly long time. But given enough time, most stars will be ejected from their galaxies, the galaxies will evaporate, and the stars that remain, the ones that didn't get ejected, their orbits will gradually decay. Gravitational wave radiation, the ripples in space-time produced by any accelerating mass, will carry away energy from their orbits, causing them to spiral slowly inward toward the galactic center. Eventually, they'll either collide with the central black hole, or they'll form a very dense cluster of stellar remnants around it. The galaxy, as a distinct structure, will cease to exist. It'll have disintegrated, its components either ejected or fallen into the center. But even that's not the end, because black holes, it turns out, aren't eternal either. Stephen Hawking showed in the 1970s that black holes emit radiation, very faint radiation, due to quantum effects near the event horizon. This Hawking radiation causes black holes to lose mass over time, to evaporate. For stellar mass black holes, this process takes an absurdly long time, about 10 to the 67th power years. That's 1 followed by 67 zeros. For supermassive black holes, the ones at the centers of galaxies with millions or billions of solar masses, the evaporation time is even longer, up to 10 to the 100 years or more. But given enough time, even these will evaporate. The black holes will radiate away all their mass. They'll shrink and grow hotter as they shrink, and in the final moments of their existence, they'll explode in a burst of radiation, and then they'll be gone. And at that point, everything that once was a galaxy, everything that once was billions of stars orbiting a common center of mass, it'll be dispersed into radiation and a dilute gas of elementary particles, spread across a volume of space so vast that the particles will essentially never interact with each other again. This is called the heat death of the universe, or sometimes the big freeze. It's the ultimate fate of the cosmos if dark energy continues to dominate. Everything becomes cold, dark, and dilute. No structures remain, no stars, no galaxies, no planets, just a vast, nearly empty expanse where the occasional elementary particle drifts through the void alone forever, or at least for timescales so long that forever might as well apply. So in the longest of long runs, all galaxies are destroyed, not by collisions, not by stripping, not by tidal disruption, though those certainly happen, but by the inexorable march of entropy, by the expansion of space, by the evaporation of structures over timescales that make the current age of the universe look like the blink of an eye. Galaxies are temporary structures, eddies in the flow of cosmic evolution. They form, they grow, they interact, they merge, and eventually they dissipate, returning their energy and matter to the universe in forms so diffuse and cold that they might as well not exist at all. But let's come back to something more immediate, more relevant to us. Because the far future, trillions of years from now, it's interesting to think about, but it's abstract, distant, almost meaningless on human timescales. What about the destruction and transformation of galaxies happening now in the current epoch of the universe? What can we learn from that? One of the most important things we've learned is that galaxies are not isolated islands. They live in groups, in clusters, even in superclusters, vast structures containing thousands of galaxies. And within these structures, galaxies interact constantly. They pass by each other, gravitationally tugging and distorting. They collide and merge. They fall into the gravitational wells of galaxy clusters and get their gas stripped away. The environment matters enormously for the evolution of galaxies. In dense environments like the centers of galaxy clusters, galaxies tend to be red and dead, filled with old stars, not forming new ones. In less dense environments, in the outskirts of clusters or in the field between clusters, galaxies are more likely to be blue and actively star-forming. The environment shapes the galaxy. It determines whether the galaxy has access to fresh gas for making new stars, or whether that gas is stripped away or heated to such high temperatures that it can't collapse and cool to form stars. And this tells us something profound about the nature of structure formation in the universe. It's hierarchical, yes. Small structures merge to form large structures, but it's also environmental. The history of a galaxy, where it formed, what other galaxies it encountered, whether it fell into a cluster, all of that matters. Two galaxies that start out identical can evolve in completely different ways depending on their environments. One might remain a vibrant spiral galaxy, forming stars steadily for billions of years. The other might fall into a cluster, get stripped of its gas, and transform into a red elliptical galaxy, dead and aging. Same initial conditions, different outcomes, because the environment intervenes. This is one of the reasons why studying galaxy evolution is so challenging. It's not enough to understand the internal physics of galaxies, the star formation, the black hole feedback, the supernova explosions. You also have to understand the environment, the interactions, the large-scale structure of the universe. Everything is connected. Everything influences everything else. Galaxies are not isolated objects. They're part of a vast cosmic web, and that web shapes them as much as their own internal processes do. And there's something else, something even stranger that we've discovered. Some galaxies, we now know, they don't just fade away or get stripped of their gas. They can be quenched suddenly, violently, by their own central black holes. Remember those supermassive black holes at the centers of galaxies? When they're actively feeding, when matter is falling into them rapidly, they can release enormous amounts of energy. And that energy, it can drive winds, powerful outflows of gas traveling at thousands of kilometers per second, fast enough to escape the galaxy entirely. These winds, these outflows driven by the active galactic nucleus, they can blow all the gas out of the galaxy in a few million years, just wipe it clean. And without gas, the galaxy stops forming stars. It quenches, it dies. And we see evidence of this happening. We see galaxies with powerful outflows. We see galaxies that appear to have stopped forming stars very suddenly. And the correlation between the mass of the supermassive black hole and the properties of the galaxy around it, that correlation suggests that the black hole and the galaxy evolved together, that they regulate each other. It's a kind of cosmic feedback loop. As the galaxy forms stars and grows, gas funnels toward the center, feeding the black hole. The black hole grows. Eventually it grows powerful enough that its outflows start to expel gas from the galaxy, shutting down star formation, starving itself in the process. The galaxy quenches, the black hole stops growing, and a new equilibrium is reached. The galaxy becomes a red elliptical galaxy, and the black hole sits dormant at its center, waiting for a merger to bring in new gas, waiting for a fresh supply of fuel. And if that happens, the cycle can begin again. This connection between black holes and galaxies, it's one of the most active areas of research in astrophysics right now, because we still don't fully understand it. We don't know exactly how the energy from the black hole couples to the gas in the galaxy. We don't know why the correlation between black hole mass and galaxy properties is so tight. We don't know whether the black hole drives galaxy evolution, or whether galaxy evolution drives black hole growth, or whether it's some complex interplay of both. But what we do know is that you can't understand galaxy evolution without understanding black holes, and you can't understand black holes without understanding galaxies. They're intertwined. And here's another aspect of galaxy destruction that's fascinating and violent: starbursts. When galaxies collide and merge, the gas in both galaxies gets compressed, shocked, heated, and then as it cools, it collapses rapidly, forming stars at incredible rates. In a major merger, a galaxy might form stars 100 times faster than the Milky Way does. It's using up its gas supply in a frenzy of star formation. These starburst galaxies, they're incredibly bright, filled with hot young stars, massive stars that burn through their fuel in just a few million years, and then explode as supernovae. So after the starburst begins, a few million years later, you start getting supernovae, lots of supernovae. And each supernova releases enormous amounts of energy into the surrounding gas. The gas heats up. It gets blown out of the galaxy in a super wind, a massive outflow of hot shocked gas carrying away not just the gas that wasn't used to form stars, but also the metals, the heavy elements produced by the stars themselves. This enriched gas gets spread out into the intergalactic medium, where it can eventually fall back into galaxies or form new galaxies. The metals produced inside stars, inside galaxies, they don't all stay there. Some of them get ejected, return to the universe at large, and the starburst itself, it's self-limiting. Once the gas is used up or blown away, the starburst ends. The galaxy has consumed its fuel in a brief, brilliant burst of activity, and what's left is a post-starburst galaxy, filled with young stars, but no longer forming new ones. These galaxies have a very distinctive appearance in observations. They're bright, but with no sign of ongoing star formation, no regions of hot gas being ionized by massive young stars. They're in a transition phase between an active star-forming galaxy and a quiescent dead galaxy. They've destroyed themselves, in a sense, through their own excessive star formation. But let's think about what all this means on a more personal level. Because we live in a galaxy, we're part of this story. The Sun is a star in the Milky Way, and Earth is a planet orbiting that star. Everything you've ever known, everyone you've ever met, every human who has ever lived, we've all existed within this one galaxy. And that galaxy, the Milky Way, it's the product of billions of years of cosmic evolution. It formed from the mergers of countless smaller galaxies. It's consumed dwarf galaxies. It's been shaped by dark matter and by its central black hole and by generations of stars being born and dying. And the atoms in your body, the carbon and oxygen and nitrogen and iron, they were forged in the hearts of stars, stars that lived and died before the sun was born. Those stars were part of earlier generations, stars that formed when the Milky Way was younger, stars that exploded as supernovae and enriched the interstellar gas with the elements necessary for planets and for life. You are literally made of stardust, made of material that was processed through the nuclear furnaces of stars, ejected in stellar winds and supernova explosions, gathered into a new cloud of gas and dust, collapsed to form the sun and the planets, and eventually assembled into the complex molecules and structures that make up your body. And that's a profound connection. You're not separate from the galaxy, you're part of it. Your existence depends on the life cycle of stars, on the chemical enrichment of the galaxy over billions of years, on the precise conditions that allowed a star like the sun to form with planets, and one of those planets to be in the habitable zone where water can exist as a liquid, and for life to arise and evolve and eventually produce beings capable of looking up at the sky and wondering about their place in the cosmos. And the Milky Way, our galaxy, it's going to be destroyed. In 4 or 5 billion years, the collision with Andromeda will transform it beyond recognition. The sun, if it still exists then, and it should, it'll have another few billion years of life left. But it'll be in a completely different galactic environment. The Milky Way's spiral arms will be gone. The galaxy's structure will be disrupted. Our descendants, if there are any, if humanity or whatever we evolve into still exists, they'll live in a different galaxy, Milkomeda. And they'll look up at a sky with fewer galaxies visible because the universe's expansion will have carried more distant galaxies beyond the cosmic horizon. And eventually, trillions of years from now, long after the sun has died, long after the Earth has been destroyed, the galaxy itself will fade. Stars will stop forming. The ones that exist will die. The galaxy will go dark. And then, over timescales almost too long to comprehend, it'll evaporate, disintegrate, return to the void from which it came. Everything is temporary, everything is transient. Galaxies are born, they live, they die. Just like stars, just like planets, just like us. But here's the thing, that impermanence, that temporariness, it doesn't make it meaningless. If anything, it makes it more precious. The fact that galaxies don't last forever, the fact that they're temporary structures in an evolving cosmos, that's part of their beauty. They're not eternal, they're not unchanging, they're dynamic, living, evolving entities, and we're privileged to exist during a time when the universe is full of them, when galaxies are still forming stars, still shining brightly, still creating the conditions for planets and life. There's an estimated 2 trillion galaxies in the observable universe, 2 trillion islands of stars, each one a unique collection of billions or hundreds of billions of suns, each one with its own history, its own story of formation and evolution. And we can study them. We can point our telescopes at them and capture their light that's been traveling for millions or billions of years to reach us. We can see galaxies as they were in the distant past. We can watch galaxies colliding and merging. We can see starbursts and quasars and all the varied phenomena that galaxies can produce. We're living in a golden age of extragalactic astronomy. And the more we learn about galaxies, the more we realize how little we actually know. We don't fully understand how galaxies form. We don't know what dark matter is, even though it's crucial for galaxy formation. We don't understand the detailed physics of how gas cools and collapses to form stars. We don't know how supermassive black holes form or how they grew so large so quickly in the early universe. We don't understand the full range of feedback processes that regulate star formation. We don't know why galaxy scaling relations, the relationships between different galaxy properties, are so tight, so universal. There are so many questions still unanswered. And that's exciting. That's what drives science forward. Every answer leads to new questions, deeper questions, more subtle questions. The universe reveals itself slowly, reluctantly, and each discovery opens up new vistas, new mysteries. We've learned an enormous amount about galaxies in the past century, but there's so much more to learn. And some of the most interesting questions are about the intersection between galaxies and life. We know that galaxies create the conditions for life. Stars produce the heavy elements. Planets form from the disks of gas and dust around stars. Life, at least as we know it, requires a stable environment, a planet in the habitable zone of a long-lived star, and that star needs to have enough heavy elements to form rocky planets in the first place. All of that depends on the galaxy having gone through multiple generations of star formation, on the interstellar medium being enriched with metals from previous generations of stars. But galaxies are also dangerous places. The centers of galaxies, where stars are packed more densely, where supermassive black holes lurk, those are probably not great places for life. Too much radiation, too many close encounters between stars, too much chaos. If a star passes too close to another star, it could disrupt the orbits of planets, ejecting them from the system or sending them into the star. And if a supernova goes off too close to a planet with life, the radiation could sterilize the surface, strip away the atmosphere, end life in an instant. So there might be habitable zones in galaxies, just like there are habitable zones around stars. Regions where stars are far enough apart that close encounters are rare, but where there's been enough star formation that the interstellar medium is enriched with heavy elements. The Sun is located in such a region, out in the suburbs of the Milky Way, far enough from the center to avoid the chaos, but in a part of the galaxy that's been forming stars for billions of years. Is that a coincidence, or is it necessary? Could intelligent life only arise in certain galactic environments? We don't know. We have a sample size of one. We know life arose on Earth in the Milky Way at this particular time in cosmic history. But we don't know how common life is, how common intelligent life is, whether there are other civilizations out there among the stars, in our galaxy or in other galaxies. The question of whether we're alone in the universe, it's ultimately a question about galaxies, about how many planets they contain, how many of those planets are suitable for life, how often life arises when conditions are suitable, how often life becomes intelligent, how long civilizations last. And that last question, how long civilizations last, it connects back to the theme of destruction, because civilizations, like galaxies, are not eternal. They rise and they fall. They're subject to catastrophes, internal and external. A nearby supernova could threaten life on Earth. An asteroid impact could cause mass extinction. Climate change, nuclear war, any number of human-caused disasters could end our civilization, if not our species. And even if we survive all of that, even if we become a spacefaring civilization spreading to other stars, other galaxies, we're still subject to the ultimate destruction of the cosmos itself, the heat death, the evaporation of galaxies, the end of structure in the universe. But again, that's trillions upon trillions of years in the future. On human timescales, it's irrelevant. What matters is the here and now, the next few centuries, the next few millennia. Can we survive? Can we thrive? Can we spread beyond Earth? ensure our long-term survival as a species? These are questions we have to answer, and they're not easy questions. They require wisdom, cooperation, foresight, a willingness to think beyond our individual lives and consider the long-term future of humanity. And studying galaxies, understanding cosmic evolution, it gives us perspective. It reminds us how small we are, how brief our existence is compared to the age of the universe. But it also reminds us how remarkable we are. We're made of atoms forged in stars. We're the universe's way of knowing itself, of thinking about itself, of studying its own history and evolution. We're conscious beings capable of wonder, capable of understanding, capable of asking questions about the nature of reality and actually finding answers. Every galaxy we see in the sky, it's a reminder of that. It's a reminder that we're part of something vast and ancient and beautiful. And even though galaxies are born and destroyed, even though everything is temporary, the fact that we can know this, that we can understand the processes that shape galaxies, that we can look out into the universe and see cosmic history unfolding, that's something worth celebrating. That's something profound, because in the end, the story of how galaxies are born and destroyed, it's also the story of how we came to be. It's the story of the cosmos evolving from a hot, dense, uniform state into a rich tapestry of structure, from galaxies to stars to planets to life to consciousness. It's the story of complexity emerging from simplicity, of order arising from chaos, of meaning appearing in a universe that, at first glance, seems meaningless. And maybe that's the deepest answer to the question of what it means for galaxies to be destroyed. It's not just about the physics, the gravity and the gas and the stars. It's about transformation. Nothing is created or destroyed, really. It's just transformed. The matter and energy that make up a galaxy, they were there before the galaxy formed, and they'll be there after it's destroyed. They'll just be in different forms, different configurations. The atoms that were once in stars will be scattered into space. Some will form new stars in other galaxies. Some will drift alone through the void for eons, but they'll persist, they'll endure. And in that sense, destruction is just another word for change. Galaxies change. They evolve, they transform, they merge and collide and quench and evaporate, but the universe goes on. New structures form, new possibilities emerge. And as long as there's energy and matter and the laws of physics, there will be something happening, some process unfolding, even if it's just the slow increase of entropy, the gradual winding down of the cosmos. We exist during a special time, a time when the universe is full of galaxies, full of stars, full of light and energy and complexity. It won't always be this way. The universe is evolving, and in the far future, it will be a very different place. But right now, at this moment in cosmic history, we can look up at the sky and see galaxies, thousands of them, visible through telescopes, each one a vast collection of stars with its own history, its own destiny. And we can wonder about them, we can ask questions, we can do science, we can build telescopes and satellites and instruments that let us see deeper into space, further back in time. We can simulate galaxy formation on supercomputers, run the equations forward, and see how dark matter and gas and stars interact to build the structures we see. We can compare our simulations to observations and refine our understanding. We can learn. And that process of learning, that quest to understand the cosmos, it's one of the most noble endeavors humanity has ever undertaken. It doesn't bring immediate practical benefits. It doesn't cure diseases or solve social problems or make anyone rich. But it expands our horizons. It challenges our assumptions. It reminds us that there's more to existence than our daily concerns, more to reality than what we can see with our eyes or touch with our hands. Galaxies are born from tiny fluctuations in the early universe, from quantum perturbations stretched to cosmic scales by inflation. They grow through accretion and mergers, pulling in gas and dark matter, forming stars, building structure. They're shaped by their environments, by interactions with other galaxies, by the intergalactic medium, by the large-scale structure of the cosmos. They're regulated by feedback processes, by supernovae and stellar winds and active galactic nuclei, by the complex interplay between star formation and gas dynamics and black hole growth, and they're destroyed through collisions and mergers, through ram pressure stripping and tidal disruption, through the eventual exhaustion of their gas supply and the death of their stars, through evaporation over timescales longer than the current age of the universe, and ultimately through the triumph of entropy, the heat death, the dissipation of all structure into a cold, dark, dilute sea of particles that will never interact again. That's the story. That's how galaxies are born and destroyed. It's a story that spans the entire history of the universe, from the first moments after the Big Bang to the unimaginably distant future. It's a story of creation and destruction, of order and chaos, of complexity and entropy. It's a story written in the language of physics, in gravity and electromagnetism, and quantum mechanics and relativity. And it's a story we're still learning to read, still discovering, still working to understand. And maybe, just maybe, that's the most important thing. Not the answers themselves, but the questions. Not the destination, but the journey. Not the final fate of galaxies, but the process of trying to understand that fate. Because in asking these questions, in pursuing this knowledge, we're doing something uniquely human. We're looking beyond ourselves. We're seeking understanding for its own sake. We're participating in the universe's attempt to comprehend itself. Galaxies are born from gravitational instability in the early universe. They're assembled hierarchically through mergers and accretion. They form stars, enrich the interstellar medium with heavy elements, create the conditions for planets and life. They're shaped by feedback from star formation and black hole activity. They interact with their environments and with each other. They collide and merge, transforming spiral galaxies into ellipticals. They can be stripped of their gas, quenched, turned into red and dead systems that slowly age. They evaporate over cosmic timescales. They fade as their stars die. And eventually, in the unimaginable far future, they dissipate entirely, returning their matter and energy to the universe in its final, cold, dark state. But right now, in this moment, galaxies are beautiful. They're vibrant, they're alive with star formation, they're full of possibility, and we're here to see them, to study them, to wonder about them. That's a gift, a profound gift, and one we should never take for granted. Because we are the universe's way of knowing itself, and in studying galaxies, we're learning not just about distant collections of stars, but about our own origins, our own nature, our own place in the vast cosmic drama that's been unfolding for nearly 14 billion years and will continue for eons to come. And that, I think, is what makes this topic so compelling. It's not just about galaxies, it's about us. It's about where we came from, what we're part of, where we're going. It's about the nature of existence itself, the fact that anything exists at all, the fact that the universe is structured and ordered and full of beauty and complexity. It's about the mystery at the heart of reality, the question of why there's something rather than nothing, why the universe has laws, why those laws produce galaxies and stars and planets and life. We don't have final answers to those questions. We may never have final answers, but we can keep asking, we can keep exploring, we can keep learning. And in that process, in that endless quest for understanding, we find meaning. We find purpose, we find connection to something larger than ourselves, something vast and ancient and ongoing. We find our place in the cosmos, not as passive observers, but as active participants, as beings capable of comprehension, of wonder, of love for the universe that created us. Galaxies are born, galaxies are destroyed, and in between, for a brief cosmic moment, they shine. They fill the universe with light and energy and possibility. And we're lucky enough to be here to see it, to be part of it, to be made of the same stuff, the same atoms and molecules and energy that make up the galaxies themselves. We're not separate from the cosmos. We're expressions of it, manifestations of its complexity, examples of what the universe can create when conditions are right. And that's something worth remembering, worth celebrating, worth passing on to future generations. The knowledge that we're part of this grand cosmic story, that our existence is connected to the birth and death of galaxies, to the formation of stars, to the expansion of the universe itself. We're here for a moment, just a moment compared to cosmic time. But in that moment we can know, we can understand, we can appreciate the beauty and complexity and strangeness of existence. And that, perhaps, is enough. That's all we can ask for. A chance to exist, to think, to wonder, to know. A chance to look up at the galaxies in the sky and understand, really understand what we're seeing. A chance to be part of the universe's long journey, from simplicity to complexity, from uniformity to structure, from nothingness to something, to everything, to this remarkable, improbable, beautiful cosmos that we call home. Now let's move on to another theory for you to reflect on. I've been thinking a lot about time lately, and the more I think about it, the more I realize that it's one of the strangest things we ever encounter in our lives. Time just flows, right? It moves forward, always forward, never backward. And that seems so obvious, so fundamental to everything we experience that we barely even question it. You wake up in the morning, the day progresses, you eat breakfast, then lunch, then dinner, you get older, never younger, and that's just how things are. But here's the thing, here's what kept me up last night thinking about this. When you actually look at what physics tells us about the universe, when you dig into the fundamental laws that govern reality, you find something deeply strange. Something that doesn't quite make sense. The laws of physics, you see, almost all of them, they don't care which direction time flows. They work just as well backwards as forwards. And yet time clearly has a direction in our everyday world. Things break, they don't spontaneously repair themselves. Coffee cools down, it doesn't spontaneously heat up. We remember yesterday but not tomorrow. Eggs scramble but never unscramble. And that asymmetry, that one-way nature of time, it's not written into the fundamental laws. It's something else, something emergent, something mysterious. And that's what we call the arrow of time, this strange, profound fact that time has a direction, even though, according to physics, it really shouldn't have to. When you think about your own life, when you reflect on your own experience of time, it seems absurd to even question whether time has a direction, doesn't it? I mean, of course it does. You were young once, now you're older, and you'll never be young again. You can remember what you had for breakfast this morning, but you can't remember what you'll have for breakfast tomorrow. That's not how memory works. That's not how anything works. The past is fixed, determined, unchangeable, a collection of facts that already happened, while the future is open, uncertain, full of possibilities. You can influence the future with your choices right now, but you can't change the past no matter how much you might want to. And this isn't just some psychological quirk of how human minds work. It's built into the fabric of reality itself. Drop a glass, and it shatters. The pieces scatter across the floor, and you'll never, not in a billion years of waiting, see those pieces spontaneously reassemble themselves into a glass and jump back up onto the table. It just doesn't happen. Things fall apart, they don't fall together. Entropy increases, disorder grows, and the universe moves inexorably from order to chaos. That's the direction of time, written into everything around us, obvious and undeniable. But here's where it gets strange, and I mean really strange. When physicists look at the fundamental laws of nature, at the equations that describe how particles move and interact, how forces work, how the universe operates at its deepest level, they find something unsettling. Those laws, almost all of them, are time reversible. What does that mean? It means that if you took a movie of particles interacting, atoms bouncing off each other, electromagnetic fields oscillating, whatever, and you played that movie backwards, what you'd see would still obey the laws of physics. The backwards version would be just as valid, just as legal according to the rules of nature as the forwards version. Newton's laws work the same way forwards and backwards. Maxwell's equations for electromagnetism, they're time reversible. Einstein's general relativity, time reversible. Even quantum mechanics, with all its weirdness, is fundamentally time reversible in its basic equations. The Schrödinger equation, which describes how quantum systems evolve, it doesn't care which way time goes. You could flip the sign of time in these equations, run everything backwards, and you'd get perfectly valid physics. And that creates a puzzle, a deep puzzle. Because if the fundamental laws don't distinguish between forward and backward in time, if they're completely symmetric with respect to time's direction, then why does the world we see, the world we live in, so obviously have a preferred direction for time? Why do we see eggs breaking but never unbreaking? Why do we see smoke dispersing but never spontaneously gathering back into a concentrated plume? Why does heat flow from hot to cold but never the reverse? The laws of physics at the microscopic level would allow all these things to happen in reverse. You could have all the scattered molecules of a broken egg spontaneously arranging themselves back into the shape of an intact egg. And that process wouldn't violate any fundamental law of physics. Each individual molecular collision, each quantum interaction involved in such a reverse process would be perfectly legal. And yet we never see it happen. Not once, not ever. So what's going on? How do we get from time reversible fundamental laws to a time asymmetric everyday world? That's the mystery of the arrow of time. And it's one of the deepest questions in all of physics. It touches on thermodynamics, on statistical mechanics, on cosmology, on quantum mechanics, on the nature of the universe itself. And the answer, when we find it, when we really understand it, might tell us something profound about why the universe is the way it is, why we exist at all, why we can remember and think and make choices. Let me try to unpack this a bit, because it's not immediately obvious why this is such a puzzle. You might be thinking, well, sure, the laws are reversible, but that doesn't mean everything has to happen equally in both directions, right? And you'd be correct to think that. Just because something is possible doesn't mean it's probable. And that word probable, that's actually the key to understanding the arrow of time. But to get there, we need to talk about entropy, about statistics, about what it means for something to be ordered or disordered. And we need to talk about a brilliant, troubled physicist named Ludwig Boltzmann, who figured out much of this more than a century ago, and whose insights are still central to how we understand time today. Think about your room, or your desk, or your kitchen. If you're like most people, it tends to get messy over time, right? You clean it up, organize everything, put everything in its proper place, and then gradually, over days or weeks, it gets messy again. Papers pile up, dishes accumulate, things get scattered around. That's entropy in action, or at least that's one way to think about it. Entropy is, in a rough sense, a measure of disorder. More precisely, it's a measure of the number of ways you can arrange the microscopic components of a system while keeping its macroscopic properties the same. A clean room is a low entropy state because there are relatively few ways to arrange everything so that it still counts as clean. Everything has to be in the right place, organized in a particular way. A messy room is a high entropy state because there are vastly more ways to arrange things so that they count as messy. The papers could be scattered in any number of configurations. The dishes could be stacked in various ways or spread across multiple surfaces, and it all still counts as messy. And here's the crucial insight, the thing that Boltzmann understood and that changed everything. If you have a system with many components, many moving parts, and you let those parts move around randomly, interacting with each other, bouncing off each other, exchanging energy, what you'll find is that the system will naturally, almost inevitably, evolve from low entropy states toward high entropy states. Not because there's some fundamental force pushing it in that direction, but simply because there are so many more high entropy states than low entropy states. It's a matter of probabilities. If there are 1,000,000 ways for your room to be messy and only 10 ways for it to be clean, and things are moving around randomly, well, you're going to end up in one of those 1,000,000 messy states much more often than in one of those 10 clean states. That's not a mystery. That's just statistics. But wait, you might say, doesn't this violate what I said earlier about the laws being time reversible? If a system naturally tends to go from low entropy to high entropy, from order to disorder, doesn't that give us a direction for time? Well, yes and no. See, here's the subtle part. Any particular sequence of events, any specific series of molecular collisions and interactions is just as likely to happen forwards as backwards. If you filmed a single molecule bouncing around, you couldn't tell if the film was playing forwards or backwards. The motion would look equally reasonable either way. But when you have many molecules, billions and billions of them, the statistics start to matter. The overwhelming majority of possible futures for a low entropy system involve the entropy increasing. Not all of them, just the overwhelming majority. And by overwhelming, I mean really overwhelming. The odds against entropy decreasing in a macroscopic system are so fantastically large that it effectively never happens. Boltzmann figured this out in the late 1800s, and he gave us what's now called the second law of thermodynamics, at least in its statistical form. The second law says that the entropy of an isolated system tends to increase over time. Not that it must increase, not that it's forbidden from decreasing by some fundamental law, but that it overwhelmingly tends to increase because high entropy states are so much more numerous than low entropy states. This was revolutionary. Before Boltzmann, people thought of the second law as an absolute, inviolable rule. After Boltzmann, we understood it as a statistical tendency. one that emerges from the behavior of large numbers of particles, one that's so reliable on macroscopic scales that it might as well be absolute, but that at its foundation is really about probabilities. And this is where the arrow of time comes from. The reason we see time flowing in one direction, the reason the future looks different from the past, is because we live in a universe that started in a very low entropy state and is evolving toward higher entropy states. The Big Bang, the beginning of our universe, was an incredibly organized, incredibly low entropy state. All the energy of the universe compressed into a tiny, tiny region, incredibly hot, incredibly dense, but also incredibly ordered in a specific thermodynamic sense. And from that low entropy beginning, the universe has been expanding, cooling, and increasing in entropy ever since. Galaxies form, stars shine, planets cool, life emerges and evolves and eventually dies, all of it driven by this increase in entropy, all of it part of the universe's journey from an unlikely, organized beginning toward a more probable, disordered future. So when we say time has an arrow, what we really mean is that entropy has an arrow. The past is the direction of lower entropy. The future is the direction of higher entropy. And all the asymmetries we see in time, all the differences between past and future, they trace back to this fundamental thermodynamic fact. We remember the past but not the future because memory formation is a physical process that creates entropy, and it only works in the direction of increasing entropy. We see causes preceding effects because causation is bound up with this thermodynamic arrow. We see irreversible processes, things that can't be undone, because undoing them would require a decrease in entropy so vast, so improbable, that it might as well be impossible. But now we have to ask an even deeper question, one that Boltzmann himself wrestled with, one that still puzzles physicists and philosophers today. Why did the universe start in such a low entropy state? That's not a given. That's not something we can just assume. In fact, it's deeply strange. If entropy tends to increase, if the universe naturally evolves toward higher entropy states, then a low entropy beginning is exactly what we wouldn't expect. It's like finding your room spotlessly clean when you haven't cleaned it. It demands an explanation. And this question of the initial conditions of the universe, this is where the mystery of the arrow of time becomes a mystery about cosmology, about the Big Bang, about why the universe is the way it is. Some physicists think the answer might be tied to gravity. See, gravity is weird when it comes to entropy. For most systems, a high entropy state is one where everything is spread out, uniform, evenly distributed. If you have gas in a box, the high entropy state is when the gas fills the box uniformly. But with gravity, it's different. A uniform distribution of matter in space is actually a low entropy state for gravity. The high entropy state is when gravity has caused matter to clump together into black holes. Black holes, it turns out, have enormous entropy. They're essentially the highest entropy objects that can exist in a given volume of space. So in a universe with gravity, the ultimate high entropy state isn't everything spread out uniformly. It's everything collapsed into black holes. And that tells us something interesting about the early universe. The early universe was incredibly uniform, incredibly smooth, with matter and energy spread out almost perfectly evenly. There were tiny fluctuations, tiny variations in density, but overall it was remarkably smooth. And if we're thinking about gravitational entropy, that smoothness, that uniformity, represents a very low entropy state. Gravity hadn't yet had time to clump matter into stars and galaxies and black holes. The universe was in a special, organized, low entropy configuration. And from that low entropy beginning, gravity has been at work for billions of years, pulling matter together, forming structures, driving the universe toward higher entropy states, states with more clumping, more structure, and eventually, in the far future, more black holes. But why was the early universe so smooth? Why did the Big Bang produce such a low entropy initial state? That's the question. And we don't have a complete answer. We have theories, ideas, possibilities, but not a definitive explanation. Some cosmologists think inflation, a period of exponential expansion in the first fraction of a second after the Big Bang, might explain it. Inflation could have smoothed out the universe, creating that uniform, low entropy initial state. But that just pushes the question back a step. Why did inflation happen? What set up the conditions for inflation? And why were those conditions the particular way they were, giving us a universe that would end up with a strong thermodynamic arrow of time? Others think the answer might involve the multiverse, the idea that our universe is just one of many, and that different universes might have different initial conditions. In that picture, we live in a universe with a low entropy beginning simply because those are the only kinds of universes that can support complex structures like stars and planets and life. In a universe that started with high entropy, nothing interesting would happen. It would just be a boring, featureless bath of uniform energy. No galaxies, no chemistry, no evolution, no observers to ask questions about time. So maybe we observe a universe with a thermodynamic arrow of time because we couldn't exist in any other kind of universe. That's a form of anthropic reasoning, and it's controversial. Some physicists love it, others hate it, and the debates can get pretty heated. And there's another possibility, one that's even more speculative, even more out there. Maybe the universe didn't start at the Big Bang. Maybe the Big Bang was a transition, a bounce, a turning point in a larger history that includes what came before. Some models of quantum cosmology suggest that time might extend infinitely into the past, with the Big Bang being just a moment of minimal entropy in an eternal cosmic history. In those models, entropy might increase in both directions away from the Big Bang, giving us two arrows of time pointing away from that low entropy moment. That's a wild idea, I know, and it raises all sorts of questions about what before the Big Bang even means. But it's the kind of thinking that physicists engage in when they try to solve the mystery of time's arrow. What's fascinating, what really gets me, is that this question about the arrow of time connects so many different areas of physics. It's not just thermodynamics. It's not just cosmology, it's quantum mechanics, it's general relativity, it's statistical mechanics, it's even philosophy and questions about the nature of existence and consciousness. Because the arrow of time isn't just out there in the universe, it's in here in our minds, in how we experience reality. Think about memory. You remember the past, you don't remember the future. That seems obvious, trivial even, but it's actually deeply connected to the thermodynamic arrow of time. Memory is a physical process. When you form a memory, you're creating a record, a physical trace in your brain, neurons forming connections, chemical changes occurring, information being encoded, and all of that is an entropy increasing process. You can't form a memory without increasing the entropy of the system that includes you and your environment. So memory only works in the direction of increasing entropy, which means it only works forward in time from past to future. If entropy were decreasing, if time's arrow were pointing the other way, memory wouldn't work the way it does. You'd remember the future and not the past. Or more precisely, the very concept of memory, of causation, of before and after, would be different or maybe wouldn't exist at all. And this raises a really deep question. Is the psychological arrow of time, the fact that we experience time flowing from past to future, that we remember one direction and not the other, is that just a consequence of the thermodynamic arrow? Are we simply entropy increasing systems embedded in an entropy increasing universe, and our sense of time's flow is just what it feels like to be such a system? Many physicists think so. They think consciousness, memory, perception, all the mental phenomena that give us our sense of time passing, they're all ultimately grounded in thermodynamics. We are patterns of information processing, and information processing requires entropy increase, and entropy increase gives us the arrow of time. But some philosophers and even some physicists aren't so sure. They wonder if there might be something more to the psychological arrow, something that can't be completely reduced to thermodynamics. After all, we don't just observe entropy increasing. We don't just see the effects of the second law. We feel time passing. We experience the flow, the movement from present moment to present moment. We have this sense that the present is special, that it's different from the past and the future, that it's somehow more real, more alive. And that subjective experience, that feeling of temporal flow, is that just an illusion created by our thermodynamic nature? Or is it something deeper, something that might tell us about the fundamental nature of time itself? Einstein didn't think the flow of time was real, not in a fundamental sense. In his theory of relativity, time is just another dimension, like the three dimensions of space. The past, present, and future all exist equally, laid out in what's called the block universe. From this perspective, time doesn't flow, it just is. The entire history of the universe, from the Big Bang to the far future, exists as a single, four-dimensional structure. Your past self, your present self, your future self, they all exist at their respective time coordinates, just as all the different spatial locations exist at their respective spatial coordinates. The flow of time, the sense that the present moves, that's not a feature of reality itself. It's a feature of how we experience reality, how we move along our world line through the block universe, accumulating memories, processing information, always oriented in the direction of increasing entropy. And this view, this block universe view, it has some strange implications. It suggests that the future already exists, that everything that will ever happen has, in some sense, already happened. It's all out there in the structure of space-time, waiting for us to reach it. Free will becomes tricky in this picture. If the future already exists, predetermined by the structure of space-time, then in what sense are our choices free? Can we change the future if it already exists? These are old philosophical questions, questions that have been debated for millennia, but relativity gives them a new twist, a new physical context. But wait, you might say, doesn't quantum mechanics change all this? Doesn't quantum mechanics introduce genuine randomness, genuine indeterminacy, making the future truly open and undetermined? Well, yes and no. Quantum mechanics is strange. It tells us that before we measure a quantum system, before we observe it, it exists in a superposition of multiple states. The electron is both here and there. The cat is both alive and dead, whatever the famous thought experiment happens to be. And when we measure, when we observe, the system collapses into one definite state. We see the electron here or there, the cat alive or dead, and that outcome is fundamentally random, unpredictable, not determined by any hidden variables, or at least that's one interpretation of quantum mechanics. It's called the Copenhagen interpretation, and it's been the dominant view for most of the history of quantum theory. But here's the thing, and this is where it connects back to the arrow of time, the process of quantum measurement, the collapse of the wave function. That's not time reversible. The equations that describe superposition and evolution before measurement, those are time reversible. The Schrödinger equation is perfectly symmetric with respect to time. But the collapse, the transition from superposition to definite outcome, that's irreversible. It only happens in one direction, from past to future. You never see a definite state spontaneously expanding back into a superposition. So quantum measurement, if we take the Copenhagen interpretation seriously, introduces a genuine arrow of time into the fundamental laws of physics. It's not just statistical, not just about large numbers of particles and probabilities. It's right there in the basic quantum processes. Or is it? See, not everyone accepts that measurement is a fundamental, irreversible process. Some interpretations of quantum mechanics, like the many worlds interpretation, say that there's no collapse at all. The wave function just keeps evolving, branching into multiple worlds, multiple realities, each one representing a different outcome. In that view, there's no irreversibility at the quantum level. Everything remains time reversible. And the arrow of time is once again purely statistical, purely thermodynamic. And there are other interpretations too, ones that try to maintain realism, that say particles have definite properties even when we're not measuring them, and that the probabilities of quantum mechanics arise from our ignorance, not from fundamental indeterminacy. Some of these interpretations, like pilot wave theory, are fully deterministic and time reversible at the fundamental level. So what's the right interpretation? What does quantum mechanics really tell us about time? Well, we don't know. We genuinely don't know. Experiments can't distinguish between these interpretations because they all make the same predictions for the outcomes of measurements. The interpretations differ in what they say is happening beneath the surface, in the deep structure of reality, but those differences don't show up in the data, at least not with any experiments we've been able to do so far. What's clear is that quantum mechanics adds another layer of mystery to the arrow of time. It's not just about thermodynamics anymore. It's about measurement, about observation, about the role of consciousness or information or entanglement, depending on which interpretation you favor. And these questions, these debates about quantum mechanics and time, they're ongoing. They're some of the most active areas of research in the foundations of physics. Let me step back for a moment and think about what we've covered, because there's a lot here, a lot of different threads, and they all weave together in this tapestry of the arrow of time. We started with the everyday observation that time flows forward, that the past is different from the future. We saw that the fundamental laws of physics don't, on their own, explain this asymmetry, because those laws are mostly time reversible. Then we turned to entropy, to the second law of thermodynamics, and we saw how statistical mechanics explains the arrow of time as a consequence of the universe starting in a low entropy state and evolving toward higher entropy. We asked why the universe started that way, and we saw that this leads to deep questions about cosmology, about the Big Bang, about initial conditions and inflation, and maybe the multiverse. We explored how the psychological arrow of time, our experience of time's flow, our memories and perceptions are grounded in thermodynamics. We looked at Einstein's block universe and the philosophical puzzles it raises about determinism and free will. And we saw how quantum mechanics complicates the picture, potentially introducing another source for time's arrow, or potentially not, depending on interpretation. And here's what strikes me, what keeps me fascinated by all this. We still don't have a complete, satisfying answer to the question of why time has an arrow. We understand a lot. We understand entropy, we understand statistical mechanics, we understand how these things give rise to irreversible processes and the flow from past to future. But the deeper question, the question of why the universe has the initial conditions it has, why there's this low entropy beginning that sets everything in motion, that's still a mystery. It might be the boundary condition of the universe, just a brute fact we have to accept. Or it might be explained by inflation, or by the multiverse, or by some deeper theory we haven't yet discovered. We don't know. And there's something beautiful about that, I think. Here we are, intelligent beings, products of billions of years of entropy, increase, and cosmic evolution, asking questions about the nature of time itself, about why we exist, about why the universe is structured the way it is. And we've made incredible progress. We've figured out so much, from thermodynamics to relativity to quantum mechanics, but we haven't figured out everything. The mystery remains, the fundamental mystery of why time points in one direction, why there's an arrow at all. Some physicists think the answer might come from a quantum theory of gravity, a theory that successfully combines quantum mechanics and general relativity into a single framework. We don't have such a theory yet, not a complete one. We have candidates like string theory and loop quantum gravity, but we don't know which, if any, of them is correct. And maybe, just maybe, when we do have a quantum theory of gravity, when we can describe the quantum state of the entire universe, including its beginning, we'll understand why time has an arrow. Maybe the arrow of time is a consequence of quantum cosmology, of the way the universe emerged from some quantum state, some quantum fluctuation, some quantum foam of space-time itself. Or maybe the answer is even stranger. Maybe time doesn't have a fundamental direction at all, not really. Maybe the arrow we see is just a feature of our particular corner of the universe, our particular branch of the wave function, our particular perspective. Maybe in some deeper, more fundamental description of reality, time is symmetric, and the arrow we experience is just an accident of initial conditions, a local phenomenon, not a universal truth. There's a thought experiment I find compelling, one that Boltzmann himself considered. Imagine an infinite universe, or even just a very, very large universe, one that's been around for an incredibly long time. In such a universe, entropy would generally be very high, nearly maximal everywhere. The universe would be in something called thermal equilibrium, a state where nothing interesting happens, where everything is uniform and boring and dead. But in an infinite universe with infinite time, quantum fluctuations, random chance would eventually produce regions where, just by accident, entropy is lower than average. These would be incredibly rare, incredibly unlikely, but in an infinite universe, they'd happen. Now here's the strange part. If you found yourself in one of these low entropy regions, you'd observe entropy increasing around you. You'd see an arrow of time pointing away from the low entropy state toward higher entropy. And you might be tempted to think, as we do, that you're living shortly after the moment of lowest entropy, that you're early in the universe's history. But actually, statistically, you'd be much more likely to find yourself at the very bottom of the entropy dip, right at the moment of lowest entropy, with entropy increasing in both directions of time away from you. That's because there are many more ways for entropy to be at a local minimum than to be consistently low for a long period. Boltzmann realized this leads to a paradox. If we take this statistical reasoning seriously, we should expect to find ourselves at a local entropy minimum, and we should expect the past to be just as high entropy as the future. But that's not what we observe. We observe a past with even lower entropy than the present, a past that extends back to the Big Bang, a genuine beginning where entropy was incredibly low. So either we're incredibly fantastically lucky, living in an absurdly improbable situation, or our universe isn't like Boltzmann's infinite equilibrium universe. It has a genuine beginning, a genuine low entropy start, and that's not a statistical fluctuation. It's a boundary condition, something that needs to be explained. This is sometimes called the Boltzmann brain problem, though that's a bit of a misnomer. The idea is that in an infinite universe at thermal equilibrium, random fluctuations would be more likely to produce a single conscious observer, a Boltzmann brain with false memories of a consistent past, than to produce an entire low entropy universe with a real past. And if that's true, if Boltzmann brains are more common than real observers in real universes, then statistically, you should be a Boltzmann brain with false memories, not a real person in a real universe. The fact that you're probably not a Boltzmann brain is evidence that the universe isn't an infinite thermal equilibrium with occasional fluctuations. It's something else, something with a genuine history, a genuine arrow of time. All of this is speculative, I should say. These are thought experiments, logical arguments about probability and cosmology, not settled science. But they illustrate how deep the mystery of the arrow of time goes, how it connects to the biggest questions we can ask about the universe. Why does anything exist? Why does the universe have the structure it does? Why can we remember and think and wonder about these questions? The arrow of time is woven into all of it. Let me talk about one more aspect of this, one more way to think about the arrow of time, and then I'll try to wrap up this long, winding exploration. There's a perspective on time that comes from information theory, from thinking about time in terms of information, knowledge, and ignorance. In this view, the arrow of time is fundamentally about the growth of information, or more precisely, about the growth of correlations between different parts of the universe. Here's what I mean. In the early universe, everything was very simple, very uniform. There weren't many structures, not many complex patterns. As time went on, as the universe expanded and cooled, structures formed, galaxies, stars, planets, molecules, life. And with each of these structures came information, patterns, correlations. The position of one star is correlated with the positions of other stars in the same galaxy. The genetic code of a child is correlated with the genetic codes of their parents. The memories in your brain are correlated with events in your past. All of these correlations, all this information, it grows over time. The universe starts simple and becomes complex, starts with little information and accumulates more and more. And this growth of information, this proliferation of correlations, it's intimately connected to the growth of entropy. At first, that might seem backwards. Entropy is disorder, right? Information is order. How can they both increase? But in thermodynamics, entropy isn't quite the same as disorder in the everyday sense. It's better thought of as the spreading of information, the dispersal of correlations. When you break an egg, the information about the egg's structure doesn't disappear. It gets spread out, encoded in the positions and velocities of millions of egg molecules, in the thermal energy of the system. The information is still there, but it's no longer accessible, no longer useful, no longer concentrated in a form we can see and use. So entropy growth is, in a sense, information growth, but it's the growth of inaccessible information, information that's been diluted, spread out, lost to us for practical purposes. And the arrow of time, from this perspective, is the arrow of information dispersal. The universe starts with all its information concentrated, localized, accessible, and as time goes on, that information spreads out, gets encoded in ever more microscopic degrees of freedom, becomes less and less accessible to macroscopic observers like us. But at the same time, the universe generates new macroscopic information, new structures, new patterns. Life is particularly good at this. Living things create and maintain local order, local concentrations of information, by increasing entropy elsewhere, by consuming energy and expelling heat, by eating low entropy food and excreting high entropy waste. We are islands of information in a sea of growing entropy, and we can only exist because the universe as a whole is increasing its entropy, flowing from past to future along the thermodynamic arrow. And maybe, just maybe, consciousness itself is fundamentally about information integration, about creating models of the world, about gathering information from the environment and using it to make predictions, to guide behavior, to survive. In that view, the psychological arrow of time, our subjective experience of time's flow, is just what it feels like to be an information processing system embedded in an entropy increasing universe. The flow of time is the flow of information, the constant updating of our models, the constant accumulation of memories, the constant march from ignorance toward knowledge, from uncertainty toward certainty, even as the universe around us marches from order toward disorder. Now, I want to be clear. This information theoretic perspective on time, it's not universally accepted. It's one way of thinking about things, one framework among several. Some physicists find it illuminating, a useful way to connect different aspects of the arrow of time. Others think it's just a redescription of thermodynamics in different language, not really adding anything new. And still others think it might point towards something deeper, some fundamental connection between information and the structure of reality, something that we haven't fully grasped yet. There's a growing sense among some researchers that information might be more fundamental than we thought, that it might not just be a way of describing physical systems, but actually a basic building block of the universe, as fundamental as matter and energy. Quantum information theory, which studies how information behaves in quantum systems, has revealed deep connections between information, entanglement, space-time, and even gravity. Some physicists, like John Wheeler, have suggested that information is the foundation of reality, that the universe is fundamentally made of information, with matter and energy being secondary. He coined the phrase "it from bit," meaning that every physical thing derives from informational bits, from yes or no quantum alternatives. If that's true, if information is fundamental, then the arrow of time might be the most basic feature of reality, more basic than matter, more basic than energy, more basic than space itself. Time's arrow might be the direction of information growth, the direction in which the universe computes itself, processes itself, becomes itself. That's a radical idea, and it's far from proven, but it's the kind of thinking that happens at the frontiers of physics, where people are trying to find new ways to understand the deepest mysteries. And we haven't even touched on all the ways the arrow of time shows up in different areas of physics. There's the causal arrow, the fact that causes precede effects. There's the quantum arrow associated with measurement and wave function collapse. There's the radiation arrow, the fact that electromagnetic waves radiate outward from sources, not inward. There's the cosmological arrow, the direction of the universe's expansion. All of these arrows seem to point in the same direction, from past to future, and they all seem to be connected to the thermodynamic arrow, to the growth of entropy from the low entropy Big Bang. But are they all really the same arrow? Or are there multiple arrows, multiple independent sources of time asymmetry that just happen to align in our universe? Some physicists think there's only one fundamental arrow, the thermodynamic one, and all the others are consequences or correlates of it. Others think there might be multiple independent arrows, with the thermodynamic arrow being the most obvious but not necessarily the most fundamental. The debate continues and probably will continue for a long time, because these are questions at the very edge of what we understand about reality. One more thing I want to touch on, because it's fascinating and because it relates to the future of the universe, to where all this is heading. If entropy keeps increasing, if the arrow of time keeps pointing toward greater disorder, what's the ultimate fate of the universe? Where does it all end? Well, current cosmological observations suggest that the universe's expansion is accelerating, driven by something called dark energy, a mysterious force that pervades space and pushes galaxies apart. If this acceleration continues, and current evidence suggests it will, then the universe will expand forever, getting colder, more diffuse, more empty. Stars will burn out, Black holes will evaporate through Hawking radiation, and eventually, in the unimaginably distant future, the universe will reach something called heat death, a state of maximum entropy where everything is spread out uniformly, where no energy gradients exist, where nothing can happen. In this heat death scenario, the universe doesn't end in a dramatic collapse or a big crunch. It just fades away, becoming colder and emptier and more boring until finally it reaches thermal equilibrium, a state where entropy is maximal and time, in a sense, stops. Not that time itself stops, not that the clock stops ticking, but that nothing changes anymore. Without entropy increase, without irreversible processes, there's no meaningful distinction between past and future. The arrow of time disappears because there's nothing left to be asymmetric, nothing left to change, nothing left to happen. That's a bleak picture, I know. It suggests that everything we do, everything we create, every thought, every experience, every bit of information we generate, it's all temporary, all destined to be erased by the relentless increase of entropy. The universe starts with a bang and ends with a whimper, a long, slow fade into nothingness. But here's the thing, and I think this is important, that heat death, if it happens, is trillions upon trillions of years in the future. It's so far away that it's almost meaningless to us, to our lives, to our civilizations, to anything we can imagine. We live in a universe that's young, vibrant, full of structure and complexity and possibility. We live in a time when entropy is increasing, but when there's still plenty of order, plenty of low entropy resources to exploit, plenty of time for interesting things to happen. And maybe, just maybe, intelligent beings far more advanced than us might find ways to postpone or even avoid heat death. Maybe we'll discover new physics, new principles that allow us to manipulate entropy in ways we can't yet imagine. Maybe we'll learn to harness the energy of black holes, or tap into other universes, or create pocket universes with new low-entropy beginnings. Or maybe, in ways we can't conceive, intelligence and consciousness will find forms that don't require entropy increase, forms that can exist even in a heat-death universe. These are wild speculations, science fiction more than science, but the point is that the future is long and we don't know what's possible. And even if heat death is inevitable, even if entropy will eventually erase everything, that doesn't make our existence meaningless. We exist now, in this moment, in this epoch of the universe where entropy is increasing and structure is forming and complexity is possible. We can think, we can feel, we can wonder, we can love, we can create. The arrow of time gives us the possibility of memory, of learning, of growth, of change. Without the arrow of time, without entropy increase, we wouldn't exist. There would be no life, no evolution, no consciousness. The arrow of time is what makes us possible. So, in a strange way, the arrow of time is both a tragedy and a gift. It's a tragedy because it means everything is temporary, everything decays, everything ends. But it's a gift because it makes existence possible, makes change possible, makes meaning possible. We are creatures of time, creatures who exist because time has an arrow, and our lives unfold along that arrow, from birth to death, from ignorance to understanding, from question to answer, even if the final answers remain elusive. And that brings me back to where I started, to the mystery itself. We've explored so much in this conversation, from entropy to cosmology to quantum mechanics to philosophy, and we've seen how the arrow of time touches on all of it. But have we solved the mystery? Have we answered the question of why time has a direction? Not completely, no. We've made progress. We understand that the arrow of time is statistical, that it emerges from the behavior of large numbers of particles and the second law of thermodynamics. We understand that it's tied to the initial conditions of the universe, to the low entropy state of the Big Bang. We understand that it's connected to our experience of reality, to memory and causation and consciousness. But we don't fully understand why the universe has the initial conditions it does, why the Big Bang was a low entropy event, why there's an arrow at all. Maybe the answer is out there, waiting to be discovered in some future theory of quantum gravity or quantum cosmology. Maybe it's a boundary condition we'll just have to accept, a brute fact about our universe that doesn't have a deeper explanation. Maybe it's tied to the multiverse, to anthropic selection, to the fact that we can only exist in a universe with an arrow of time. Or maybe the answer is stranger than anything we've yet imagined. something that will require us to rethink our basic concepts of time, space, causation, and existence. What I find beautiful, what keeps me up at night thinking about this, is that we can ask these questions at all. We can wonder about the nature of time, trace the arrow back to its origins, explore the connections between entropy and existence, grapple with the implications for reality and consciousness. And even if we don't have all the answers, even if the mystery remains, the process of asking, of exploring, of trying to understand, that process itself is meaningful. It's what humans do. It's what we've always done, looking at the world, at the cosmos, at ourselves, and asking why. The arrow of time is, in a sense, the arrow of our existence. We are born, we live, we learn, we grow, and eventually we die, all along the one-way street of time, all carried forward by the current of entropy increase from the Big Bang to whatever comes next. And in our brief moment of existence, in this brief window where entropy is increasing but structure still exists, where complexity is possible and consciousness can emerge, we get to witness the universe, to be part of it, to think about it, to marvel at its mysteries. And maybe that's enough. Maybe the mystery of the arrow of time doesn't need to be completely solved to be appreciated. Maybe it's enough to understand what we do understand, to know that time flows forward because of entropy, that entropy increases because of statistics, that statistics matter because of initial conditions, and that initial conditions might tell us something deep about the universe's origins, about quantum cosmology, about the nature of reality itself. Maybe it's enough to know that we're part of this vast cosmic story, this journey from low entropy to high entropy, from simple to complex, from beginning to end. And in the meantime, we keep asking questions. We keep doing experiments, developing theories, exploring possibilities. We keep pushing at the boundaries of knowledge, trying to see a little further, understand a little more deeply. Or, because that's what it means to be conscious, to be aware, to be a thinking being in a universe with an arrow of time. We remember the past, we experience the present, we anticipate the future, and we wonder why it all works the way it does. The arrow of time points forward, always forward, carrying us along with it, from moment to moment, from question to answer, from mystery to understanding, even as new mysteries emerge. And that forward motion, that irreversible flow, it's not just a feature of physics, it's a feature of existence itself, of what it means to be, to become, to live in a universe that started simple and became complex, that started ordered and became disordered, that started with a bang and might end with a whimper. But in between, in this middle chapter, in this era of stars and galaxies and planets and life and consciousness, gives us the gift of asking why.